Okay, simple harmonic oscillator has a period of 0.0318 seconds, a mass of 0.185 kilograms, moves with an amplitude of 6.5 centimeters, right? 0.0650 meters, right? Find omega first. Okay, I'll do that. Okay, so omega is going to be, I'll put it up here, right? Omega is 2 pi divided by seconds, right? So that's 2 times pi divided by 0.0318. Store that in A. And I get 197.58, 58, and then 44 indeed, radians per second. Okay, I'm going to store that in W. Okay, so then A says, what's the total energy of the system? Okay, well, the total energy, I'm going to use the formula that's called the total energy formula, right? So ET is equal to 1/2 m omega squared x naught squared, right? And all this is, by the way, is it's 1/2 mv squared, because remember the maximum velocity is omega x naught, right? And so what they did was they put in the maximum velocity. So this is the maximum kinetic energy that we're calculating actually. But the reason that it's the total kinetic energy is that, of course, when it's going the fastest, it's passing equilibrium. And when it passes equilibrium, it has no potential energy. X is 0, right? So 1/2 kx squared is 0. Okay, so let's just plug in numbers. So 1/2, our mass is 0.185 kilograms. Our omega squared is 197.5844 radians per second squared. And then our amplitude is, what is it, 0.0650 meters squared. Don't forget to square that, baby. Okay, so I'm going to go 0.5 times 0.185 times alpha W, right, which is our 197.5844 unrounded, okay, squared times 0.065 squared. And the answer is 15.257 joules, which would be 15.3 joules. Now, the next questions are rhetorical, right? What's the maximum potential energy? Well, that's its maximum kinetic energy. When it's got the maximum potential energy is when it's at the edges. Well, when it's at the edges, its velocity is 0. Because if it's not 0, it's not quite at the edge, is it? Right? It's on its way there, or it's returning from the edge, right? So it has no kinetic energy when it has maximum potential. So therefore, all the energy, all of this energy that was potential or kinetic has to have turned to potential, right? So the answer for B is exactly the same as the answer for A, right? And then D, what is the, maximum kinetic energy is B, right? So yeah, this is the maximum kinetic energy. It's also the total energy. It's also the maximum potential, right? And then D says when the mass is displaced only 0.34 meters from equilibrium, what is the kinetic energy? Well, let's use the formula for kinetic energy, right? Now, I hope you recognize that this is just, the formula is just 1/2 mv squared, right? And then V, we substituted V for omega square root of x naught squared minus x squared, right? If you substitute that for V, you end up with this, right? So it's not a magic formula. So let's plug in, right? 1/2 times 0.185 times 197.5844 squared times 0.065 squared minus 0.034 squared. Yeah? Because that's where we are, is there, right? Our maximum is there. That's our x naught, right? Okay, so I'm going to go second entry. And I'm so lazy, I'm going to put parentheses in there. Okay, minus 0.034 squared. Okay, so I'm typing 0.5 times 0.185 times omega squared, right, which is 197.5844 squared. times parentheses 0.065 squared minus 0.034 squared. And I get 11.08. 0.08266 joules. So that's 11.1 joules, right? Okay. And then it says, what is the potential energy? Well, potential energy is going to be, if the total energy is this, right? And this much, if this much energy is kinetic, right? And kinetic plus potential has to add to this, then total energy minus kinetic must be the potential energy, right? So all I'm going to do is I'm going to go 15.257 minus 11.08266 joules, right? So that's total energy minus kinetic equals potential energy, right? These are J's that I'm putting there. It's not a mystical number, right? Okay. So I'm going to subtract the 11.08, right? Okay. And then 15.257. And I get 4.17 joules. Okay, that's how much must be potential energy, right? So the idea is that this plus this equals that, yeah.